We're going to start. We got it. All right. And we have actually a good crew already here, Dennis. People are lining up to hear this talk. I'm pleased to have Dennis Wingo here, noted lunar expert. And he's
lunatic.
Yeah. Lunatic, an official lunatic. And he has, I think, quite an interesting presentation to go through. And so I'm going to turn it over to Dennis. Dennis.
Thanks, Bruce. Really appreciate everybody that's here today. People from all over the world. Hello to Israel. Hello to folks from ESA and everyone. And, you know, everybody wants to go to the moon now. We've had already an amazing past 12 months with our friends from China with Chang'e 4. And its rover roving the moon right now on the lunar far side. We have our friends from Israel, Space IL, that they have Israel's first lunar lander on the way to the moon even as we speak. And I believe we're entering an exceptionally exciting era. And coming from one of the ones who carries many of the scars from the battlefield, you know, there's an old saying that an overnight success takes 20 years. Well, this has been 50 years almost since our friends Buzz Aldrin and Neil stepped foot on the moon, and the world was changed. And sometimes it takes time for these things to gestate. And before I get into the technical part of the presentation, I'd like to speak on philosophy first. I have a book in my library. I collect books. And one of those books is called The Last Best Hope of the Earth. It was a book written in 1940 about the philosophy of the coming war. It was written for an American audience in 1940, before World War II started, and it gave the rationales of basically why we fight, why we need to fight, why, and it was exceptionally interesting. There was only 2 billion people on the earth at that time, and it was already talking about how commerce, global commerce, had changed the world in the preceding few centuries, and how the ability for food to move here and there had completely changed the world and had made things better. Life expectancy had increased, and that part of the rationale there was that you had people that wanted to hoard, and you had people who wanted to create, as we would call it today, walled gardens. Yeah. That they control to the detriment of everyone else. And those forces have not receded from our world. We live in a world now of almost 8 billion people. We still live in a world of a single world of resources, and the resources of a single planet. And going back to the 1970s, there was a very influential book called The Limits to Growth. And one of my mentors, Dr. David Webb, who's one of the founders of the International Space University, he and I were talking about it, and David told me that he had been on the board of directors of the group that funded the study by MIT that led to the book Limits to Growth. And that he met with all these people, and a lot of them were European bankers who were very, very high-level people. And David asked them, because he was already a very big space supporter at the time, and you have to remember when that study was done and that book was written, we were in the middle of the Apollo landings. So this was not fantasy. It was not science fiction. We were actually walking on the moon during the time this book was written. And he asked them, after this was done, he says, you have a very doom and gloom view of the future here. Why are you not considering space? He says, oh, we don't think that has anything to do with our future. Wow. And so I would posit today that the last great hope of the Earth is in space. And as I talk about in the tagline of my book, Moonrush, we go to Mars to take our civilization there. We go to the moon to help save our civilization here. And I want to talk a little bit about resources here because I just read an article yesterday. Bill Gates Foundation and a bunch of investors have just invested in a new AI platform for resource prospecting here on the Earth.
Really?
And ostensibly the reason for this is that all of these advanced batteries, like in a Tesla, or all of these battery cars, or the power walls, all this rely on cobalt. And 3/4 of the world's cobalt comes from the Congo. And they basically call this like, you know, they talk about in some parts of Africa blood diamonds. And my wife and I kid people, says, oh, that's a nice diamond. How long did it take you to wipe the blood off? We basically have today blood cobalt. Because in many parts of the world that have the resources, they do not have the governance structure in the countries and all to be able to effectively control and to make sure that their own people are taken care of. And there are many, let's call them sources, people that would exploit that, countries that would exploit that for whatever reason that actually benefit from the corruption. And I tweeted back because they were just tweeting about this new AI platform, and I tweeted this last night out. It says, well, I know where there's millions of tons of cobalt right now. Mm-hmm. That millions of tons of cobalt is sitting on the moon from asteroid impacts. And this was the fundamental thesis of my book, Moon Rush, because I am an acolyte. I am a disciple of Dr. John Lewis, who wrote the book Mining the Sky. And in that, Dr. Lewis talks about nickel metal asteroids, that there are, you know, they're mostly iron and then nickel and about 1 or 2% cobalt. And then there's the platinum group metals. And that the resources of these are literally billions and trillions of times greater than on the Earth. And then I took that thesis because Dr. Lewis always called the moon the slag heap of the solar system. And I said, well, John, that slag heap, 3 out of every 100 of those craters are your favorite rocks up there. Because this is the case on the moon, and that we know this from the statistics, about every 3 out of every 100 is a nickel-iron impactor. So if you look at the moon, you look at any image of the moon, 3 out of every 100 of those craters is from nickel metal asteroids. Well, I've always had this debate with my friend Harrison Schmidt, and Harrison said, well, all of that gets blasted off the moon. I said, well, Harrison, if you look at your own results from Apollo 17 and Apollo 16, especially in Apollo 16, which is highlands. The lunar highlands is the older terrain, to improperly use the word, of the moon. And the Mare, so anywhere you see light colors on the moon, that's old terrain. And the darker terrain is iron-rich basalts. And these iron-rich basalts are weathered over time by the solar wind, and so they turn dark. But the lunar highlands is mostly aluminum-rich and magnesium-rich. And so that they don't weather under hydrogen bombardment in the same way. And so that's why the highlands region of the moon is lighter. But so it's much older terrain than these lava-filled basalts in the Mare. And if you look at Apollo 16 samples, there are many samples of the regolith. Many of the glutinates have up to 1, even 2% nickel iron. And when the Apollo, and this is one of the things we're going to advocate here, when the Apollo samples were looked at, and still the vast majority of the work on the Apollo samples was done in the late 60s to mid 70s. There has not been that much analysis work done on lunar samples since that time, and they were mostly interested in the origins of the moon, and so they kind of, oh, this is meteoric iron, and they didn't further investigate it. And so we have kind of let's call it a skewed look at some of the lunar resources, and the same thing happened with lunar water. Because there were many Apollo samples, especially the ones in the Mare region, the highlands, wherever, that had what they called anomalous water content. Some of these up to 200 or 300 parts per million, which is 200 or 300 grams per ton, even in the equatorial region.
And not hydrogen, you're talking about actual water.
No, this was actual water, and they dismissed it, and they said, oh, this is just Houston humidity, because, you know, these guys walk out the door and it's Houston humidity. But we now know from Carly Peters and the work of the Moon Mineralogy Mapper, from Galileo, from Lunar Reconnaissance Orbiter, from Kaiguga, the Japanese mission, that this water is real. So,
get L-Cross.
And well, L-Cross was a further validation in that it went to one of the permanently shadowed areas, and they got all kinds of hydrocarbons and volatile content and all. And so our view of the moon, there are many discussion lists. And one of these discussion lists is they talk about, well, we looked at this in the 1970s and there's nothing there. Well, it's not the 1970s anymore. And so I'm going to discuss this and kind of some of the steps going forward, because it is my premise, and this is why I call this the steps to lunar industrialization. Because the moon, in my opinion, is the first place in our solar system. And for those of you who have not watched this yet, I advocate that absolutely everyone watch the incredible television program available on Amazon Prime of The Expanse. And The Expanse talks about a time about 200 or 300 years in the future where we're actually actively exploiting and using the resources of the solar system. And, you know, it carries our conflict zone out there, which is probably the case. But it talks about a solar system-wide civilization and how that has helped maintain and expand humanity. And so this is, you know, we have this today, and we still have what I go back to and call the 1970s gloom and doom viewpoint is very strong. It's even strong. In some ways, it's stronger today than it was in the 1970s, in that we have 12 years to save the world, or we have to do this, or we have to do that. Well, there are always alternatives. And even in the 1970s, and I was very influenced by this because I was a teenager in that time, and we're all, when we're teenagers, we're going, oh my God, we're doomed, the world's going to end. But there was this magazine called Omni. There was this guy by the name of Jerry O'Neill, and Jerry was talking about a positive future, and Jerry was talking about, you know, habitats and cities in space. And there's this guy named Jeff Bezos that kind of did the same things. And so we live in a different age now. We have people who were brought up on the more positive view, and I consider my friend Elon Musk, I consider Jeff. There are so many, and so this is why we're in a time where what we talked about that was science fiction 40 years ago, that now we have done all of the hard work. Paul Spudis' work, and I give a call out to my friend Paul, who knows everything now, who beat his head against this wall for 30 years. It took that long for people to even accept the premise of the water on the moon, whether it was in permanently shadowed areas or not. So I'm going to go forward here, show you some slides, kind of go through them fairly quickly. And then, do we have a Q&A?
Yeah.
And then I want to open it up for Q&A, and we consider further.
And by the way, we're broadcasting this from the space portal, so there are several of us in the room here with Dennis. So
yeah, we're here at NASA Ames at the Commercial Space Portal, and Dan and Bruce and Lakshmi and just an amazing group here that they themselves have made a major contribution to help bring about a positive future for all of us. So, you know, I talk about my company, but this is what I've been doing for a very, very long time. We've been involved in this kind of research since the 1990s. Even before then, I was one of the original, not founders, but very early members of the Lunar Prospector team, which was the world's first private mission to the moon. We wrote the RFP at the Space Studies Institute in 1989 when Jerry was still alive, and the Space Studies Institute at that time was very strongly supported. And Jerry himself is the one who gave his personal kind of imprimatur to commercial development of the moon. He completely changed his kind of mindset and go, we have to go to the moon commercially because we can't depend on the government. And Jerry came to this realization actually very early. And so Lunar Prospector was designed specifically, and we chose that word specifically to give the mindset that we are prospecting the moon. We sent a gamma ray spectrometer on the mission to find the hydrogen to help confirm the water. There was magnetometers. All of our experiments on Lunar Prospector was designed that way. And then there was a guy by the name of Alan Binder from Lockheed Martin who picked that mission up. And NASA Ames, Scott Hubbard here at NASA Ames supported that mission. And so Lunar Prospector was managed here out of NASA Ames and was the first orbiting mission to go back to the moon, along with Clementine from another NASA Ames Center director, Dr. General Simon Pete Warden, sent a military mission to the moon because Pete, being the kind of person Pete was in the military, you know, we can't test these anti-ballistic missile systems in Earth orbit, but it doesn't say anything in the rules about testing it in lunar orbit. So that was Pete's excuse to spend $80 million of the taxpayers' money through the Department of Defense to send a mission to the moon. It's still the only mission to the moon that the U.S. military has ever sent.
Outside of the lunar orbiters, but yeah,
yeah. And so NASA Ames has a long and storied history of kind of guerrilla lunar exploration here at NASA Ames.
Lunar hackathon.
Yeah, lunar hackathon. Yeah, and so we're very happy about all that. So the fundamental principle today, and we're actually having these active discussions in very interesting areas of the government, is leadership. You know, we've been talking about this forever. We've got dozens and dozens and dozens of studies. Let's get going. The essence of leadership in the military says when you're presented with a whole bunch of options, pick one and go, because part of the problem is you can sit there and gaze at your navel forever and not do anything. And unfortunately, we've done a lot of that. So it's time to go. And so what we talk about here, it's much more industrially focused. The science community wants to go to the lunar South Pole. God bless them, because that's where we find out about the origins of the moon. But our premise here is to go more towards the North Pole. And so Chandrayaan, I've already talked about this. We have enough remote sensing data. It's time to put, and Paul Spudis and I talked about this, it's time to put wheels on the ground.
Yep.
Followed by boots. And so the goal is actually industrial development. What does industrial development mean? It means developing industry. It means we actually want to take the materials of the moon and use what is actually the greatest resource on the moon, which is the vacuum, combined with the materials that are on the moon, and then use that to create products, both for use on the surface, for export from the moon, and even manufacturing to help us expand into the solar system. And so we call this, and in one of our previous incarnations, we call this the spiral development. Admiral Steidl. And so you take and you have a vision for where you want to be. We want an industrial site, but you got to go back step 1, step 2, step 3, step 4. So that's what we're going to talk about today. So for industrialization, you want to stay away from where the scientists want to be, and we're cool with that. And I'm going to show you a little video here. This is a flyover of the floor of Peary Crater to a landing at the rim of Whipple Crater, which is the northern peak of almost eternal light. And so right now, when you're seeing this, all of these craters that are below you, even though they kind of show sun, some of them have sun, the water, the permanently shadowed regions with the water are in the floor of all of these craters in the floor of Peary Crater itself. And so we're flying here in this big crater that you see here. This is Whipple. And Whipple is also another crater that has probably a large area of water. And kind of in some of our visioneering, we want the moon's first industrial civilization, kind of really big city, to be in the floor of this crater building back up after we've already mined it. And so right here where we're flying over now, this is where the peak of eternal light is. And this is accurate, excuse me, because this data is from Lunar Reconnaissance Orbiter. And it comes up here, and there's this very cool, interesting thing. Excuse me, I have to drink some water.
Looks almost like a monolith, Dennis.
We call it a lunar menhir. This is actually in the data from Lunar Reconnaissance Orbiter LOLA data. So we go here, we want to build up at that site, and a lot of people talk about, and NASA talks about right now, we want to land in all these places. I absolutely agree, because we need to learn more about the moon. Someone gave our previous president a really bad line. We've been there and done that. No, we haven't. It's like telling Christopher Columbus after their first mission, or after He made it to Africa, okay, we've been there and done that. We don't need to do this anymore. So we want to go many places, but each mission costs a lot of money if it is led from the Earth all the way there, because the resources, the hardware, all of this stuff. So what we want to do is we want to land at a site like Whipple, the rim of Whipple, build up from there, obtain some of the water, and then we can do suborbital hops at a small fraction of the price that we can from any other place. And so this is step one when we start getting back to the moon. And so the very first mission, and we reimagined, this is a lander, and for those of you who know your space science, this lander right here looks very familiar. We reimagined the Lunar Surveyor mission, which NASA landed successfully 5 times in the 19th on the moon. And so we talk about repurposing and rebuilding this lander, because guess what? We know it works. And what most people don't know, there is one of the incarnations of the Surveyor that had a rover. So you land you land and you have a beacon, so you start to build up infrastructure. You have a rover that goes around and looks, sees where the good places are. It's called site planning, where you actually are planning for your future site, and you do that work, and so you understand your terrain, and then you move on from there.
Well, and this is set up so that Surveyor, which originally were designed to survive partly through the lunar night, but you have this
Well, also in the lunar polar regions has a much more amenable thermal profile. When the Surveyors landed in equatorial regions, it's very hot. It's 175 C in the day and minus 175 C at night. In the lunar polar regions, it's much closer to being about an average of minus 40 C. And so it's a much more survivable terrain to land in and start with. And then we have much better electronics now, batteries, solar arrays. And so it's much easier to design a lander that will survive multiple nights. And so that's what we're looking at. And so the rover goes around, and we can land multiple rovers. There's a lot of fun we have. Right here, this is our ground truth from the Whipple crater area. You see here Peary in the foreground, and then you see Peary that you saw in the video towards the 1 o'clock. And so we know this terrain. We have plenty of data. And the nice thing about Peary crater is that this is flat terrain over a distance of almost 100 kilometers. And in the bottom of Peary are all of these small, permanently shadowed craters. Guess what? That's where the water is. And if you look here in the lower right, all of these circles is around, and this is from Chandrayaan and Paul Spudis's work. This is where the CPR indicates where there's water, and this is all in the rim of Peary, not in the rim, in the floor of Peary, and in that general area. So we know this now. And then on the lower left, that's a terrain map of the bottom of Whipple, and it shows you what Whipple looks like inside as well. Now, this is the Whipple site details, and I want to give another plug for NASA Ames. It's called Moontrek now, I think. Is some great software, even though they're trying to improve it. You know, there's a rule of software. good software is always improved into the point of unusability. And certainly this is happening, but it is a great package that allows you to do a lot of site planning and a lot of fun work. And this is the area where the permanently lit area is for Whipple. And here's a nice terrain map and a altitude profile. So that's the area where we want to start. This right here also from Moontrek shows you this is the vertical terrain versus what's called the lunar centroid. Right here, this is what's called the lunar, this is sea level on the standard terrain of the moon. And so the floor of Peary is 2,800 meters average below that, and you can see this is a cross section, so you see some of the permanently shadowed craters. That's 879 meters, so that's a total of about 3,600 meters to the top here. This is where Whipple is. Now over here, this is very interesting as well. This is the interface between Peary and Byrd craters. That's another area, and what we talk about is to be able to put, it's called ultra-wideband radio, and I'll talk about that more in a second. And so you could actually, instead of requiring to have a GPS in lunar orbit, you put some landers around the rim and broadcast radio in there, and so you can do autonomous operation, terrain management, the whole 9 yards. And then you see here in the bottom, it's 91 kilometers from the rim of Whipple all the way across to the top of Byrd. So this is, we know this is good data. Now this is why I advocate for industrialization, much more the north than the south. Right here is still the same lunar sea level, but this is where the water is at the bottom of Shackleton Crater. Well, this right here is the top of Malpert Mountain, where the permanently sunlit is. That's 16 kilometers, excuse me, straight down at a much sharper angle than in the north. And over here, this is the other permanently lit area. And so this is just very, very rough terrain. And it's not going to be easy to get around in that terrain in the southern polar region. So I want to go in an area where it's much easier to navigate. So that's why I advocate lunar north. Now here, we call this local robotics positioning for swarm applications. We want to have swarm robotics. This was actually done by NASA JSC. This is some work that they did with ultra-wideband radios, and that's out of Huntsville, Alabama. It's time domain. And so you can put these around the tops of these craters, and then there is three-dimensional positioning. And so you can have swarms of small robots working together to either get the water, to do terrain, to measure whatever you want to do, move materials. You can do that without having to spend billions and billions of dollars building a lunar GPS. And so this is a fundamental difference between a science outpost and an industrial outpost. And so this is what we talk about. And so we want to start with these reconnaissance missions. We want to learn the terrain. We want to figure out what's there. And then this is what we want. We want lunar industrialization. This is from a activity that we did with NASA Langley in 2006, where we actually have and we center landing pads on the moon to deal with an issue that Dr. Phil Metzger has identified relative to when you land in an area of unconsolidated material, you can throw detritus all across the moon. And then one of the resources that is absolutely vital for us to protect is the vacuum. Now, for hundreds and hundreds of landings, we're going to actually build an atmosphere on the moon. And we really don't want that. So if you start out with a centered landing site, you remove the detritus problem, and then you can build up. Now, over here on the left, these are what we call power towers, and we developed this 15 years ago now in the lunar polar regions to be able to have power. Because what is the first thing an industrial civilization needs? It's power. And so these landers, which could fly either on a Falcon Heavy Delta IV Heavy, that was when I first did this, or a new Glenn or new Armstrong, we can put 100 kilowatts on the moon in a single landing. And so we really want that. And so we did a paper as a result of a big conference we had in 2014. It was supported by Dan, Steve Jurvetson from Draper Fisher Jurvetson. We basically get 67 kilowatt per hour average power from a 100 kilowatt lander landed there at the rim of Whipple. And so now I can start building a power budget. And one of the problems with our space station right now is power limited. And so we want to have robust power on the moon. And I actually worked with NASA and JSC on the Desert Rats. And so they have all these rovers and stuff out there. They had 4 100 kilowatt generators there to run the site. Well, if you look at NASA's plans, they may have 20 or 30 kilowatts or 40 kilowatts on the lunar surface. That's fine for science, but you're not going to do industry with that level of power.
Well, and just for people online, the space station has how much power right now?
Space station, solar arrays are 75 kilowatts, and they have about 85 kilowatts total with the Russian solar arrays, but that only means they have about 35 kilowatts average power.
So one of your power towers is more than...
One of the power towers is double the effective power of the entire space station. And we want a bunch of them. We'd like to put 10 of them on the lunar surface. So the first task, and this comes from something that Larry Taylor did, one of our previous generations of lunar scientists, that God bless him, he's no longer with us. Larry is able to get regolith out of JSC, real regolith, and he gets to play with it in his lab, and he says, I wonder what would happen if I stick this in a microwave oven and turn the microwave on. Well, what Larry found out is that he could take any regolith sample on the moon and heat it to 2,000 degrees centigrade in 30 seconds in the microwave.
And center it.
And what that does, that centers it, that turns it into basalt. And so we developed, and I gave this back to Larry, you see right here, this is a grater, so it grades the surface, and then you have these microwave emitters behind it that centers, it gives you the high temperature, and you center the surface. And you can do this up to 1 meter thick with 50 kilowatts of power, and that's the effective EIRP at 2.4 gigahertz for something like this. And so now I can center a landing site. And so that's what we developed. And so that's what you want to do. And so this is what you get, along with some rovers to move dirt around or regolith around and stuff like that. And so this is how we came up with the initial outpost. Again, this is work we did in 2006 for NASA Langley, and I have an entire 114-page report on that we need to put online somewhere around here. It used to be online at the UAH library, but I don't think I have it online anymore. NSS may have a copy of it. So now we add capability. We want to add landers. We want to add, and this is when the segways were popular that we did this. And so you have the NASA robonaut on a Segway on the moon, moving around doing stuff. This right here in the upper right, this is a vacuum induction furnace. Well, guess what? You got a lot of vacuum on the moon. And so you added electrical power as an induction furnace, and you actually, after beneficiating the soil to get the meteoric fragments out of it, so now I can actually pour metal.
Yeah.
And this is
different types of
metal.
metal.
And this is without advanced processing. I just get a magnet, I pull the metals out, I stick them in a vacuum furnace, and melt it and pour it into molds, and so that gives me structures. And guess what? You need structures. Versatile robotics. And this also goes to lunar landers. The way that we design lunar landers today is stupid. Because we design a lander, it has a bunch of dry mass, we have a payload, we land it on the surface, we take the payload off. Well, going back to Werner von Braun, they actually use the tanks and the pieces of the lander as effective equipment on the moon. And so now I don't have a dry mass. I have an entire lander
that you make use of.
That we make use of. And so any work that you do on landers needs to incorporate this modularity I want to take the computers off and be able to have the computer from a lander be the computer for a rover, or the computer for my environmental system on the moon. It's called multiplicity. It's the way we do stuff here on the Earth. Here on the left, this is a gantry crane, originally developed by Boeing for a 1990 Space Exploration Initiative proposal that can move heavy payloads. These right here, these wheels on the bottom was actually developed by NASA Ames, a concept called the mule. And then this is what we also have. This is what's called a high mobility rover. Well, this was originally developed in 1973 by a company called Eagle Engineering. A bunch of guys that left NASA JSC after the Apollo program did amazing work in preparation for the Space Exploration Initiative. It's called LOTRAN, very high mobility. The problem we have, if you look at U2, which is the Chinese rover, or our rovers on Mars, they're very low mobility. The Russian Lunokhod could move at 20 kilometers an hour. Lunokhod moved over 31 kilometers. The American lunar rovers went 45 kilometers. We need high mobility on the moon because guess what? We can operate them via telepresence from the Earth. And here's why. This is the traverse from the rim of Whipple here to the bottom of Peary to the first permanently shadowed place where the water is. The slope angle is no more, it is not bad. It's no more than about 22 degrees. Actually, in this one, it's 17 degrees. And so this is the slope histogram of that route, and it's only 16 kilometers. If I have a high mobility rover, I could get there in 2 or 3 hours. And so I have this system where I have the power landers that actually recharge the rovers. And so the rovers have enough battery to go all the way down and then come all the way back up, because, you know, you can't waste all your time making sure your rover's in the sunlight all the time so that you can keep your power budget. That's another thing that really limits today's rovers. They have to carry their power supply and their solar arrays with them, and so they're fundamentally limited. Look what happened to Opportunity after a dust storm. We lost it. Yeah. So, and then you take, and today with additive manufacturing, one of the things that we know, and I'm going to wrap up here fairly quickly, is that the distribution of the size of the metal particles on the moon is actually very close for what we want for direct input for 3D printing with metals. And there's 3D metal printing all over the world now. And so this is a new technology that's only come around in the last 10 years that's going to transform the way we do the moon. This is where they're actually doing this with rock. NASA did this. Metal finds in the regolith, Apollo finds. And I'll put this whole presentation online as well, and it'll be part of this recording. So we know all of this already. This is direct metal laser sintering. These are the products that we get. Imagine not having to carry your rovers. Imagine how stupid it would be to carry a bulldozer to the moon. Well, 90% of the mass of a bulldozer is raw metal. Right. Why not carry the motors, the actuators, and the things you need like that on cargo missions to the moon? And then because people talk about, well, the metal meteorites, you don't want to bring the iron back. Of course not, but they make great bulldozer blades. So this is the difference in thinking. And they're actually making entire cars with 3D printing. We know about this now. This is MX3D in the Netherlands, that they're actually building bridges, 3D printing bridges directly with metals in Amsterdam. And MX3D is already thinking ahead to the moon themselves. So we love those guys over in the Netherlands. Lunar development requirements, power, and then this is where we want to go. The advanced space is just the beginning. Why do we want an advanced space? Well, we've got a huge problem. I'm doing a study right now about cosmic rays. And I'm telling you, the cosmic ray environment is a lot worse than what a lot of people want to believe. Yeah. What if I could build in lunar orbit? I take the gateway, instead of putting it in a useless orbit, put it into low lunar orbit, and have it as the beginning of a manufacturing facility in lunar orbit to build interplanetary vehicles that look a lot like the ones in the movie The Martian. That's actually a beautiful design. And then you have a rotating structure with plenty of shielding for the crew, and so they don't have the problem with gravity. They don't have to worry about not ever having babies after they come back. And so we start to build an interplanetary economy that starts to look like the Expanse. And that's what we want. You know, we want Earthers and Martians and Belters. We want those guys to be fighting, not fighting here on the Earth. And so I'm opening up for questions now.
Well, and just for my people online, okay, you're muted, so you have to unmute your microphones. And if you have trouble chiming in, raise your hand. I'll be watching. You raise your hand, and I'll call on you. So, but at this point, let me turn it over to questions, comments for
Dennis Wingo. Dennis, can you hear me?
Yes, I hear you. Who is this?
Dallas being on.
This is
Hey,
Dallas.
hey,
How
buddy.
are you? Oh, crap.
I'm here. I can hear you.
Okay, so all of this stuff is great, but what's the cost of the water you're going to mine from the moon for me? What's it going to cost?
Don't know yet. But here's a number. Right now, our friend George Sowers uses a number. What I think he uses a number of about 1,000.
He's on the line.
No, he says 300. He will buy it at $300 a kilogram.
But
yeah,
500.
Unfortunately,
he's on the line.
Yeah, and I love George to death, but I think that number needs to be higher, at least initially, especially if I'm on the surface. A lot of the water I want to use on the surface because I want the hydrogen economy on the moon. Our rovers should be fuel cell rovers because it has a lot better power density. And so I'm using a lot of water on the surface, and then I want water for a suborbital hop. And I'm going to go to George's thesis here. I love George's thesis, but right now, if NASA's doing a sortie to the moon for science, it's going to cost $2 billion. But if I build up an infrastructure on the surface and I do a suborbital hop and I have 10 tons, say 10 tons of water, I can afford to sell that water, and NASA can afford to buy that water for $15,000 a kilogram and still do a sortie mission to anywhere on the lunar surface and back for less than 1/10 of what a dedicated sortie mission would be. So, and my concern about George's approach is that he's doing the same thing that we used to try to do with solar power satellites, to try to sell the power for 3 cents a kilowatt hour to compete with coal. Well, we know now that there's many areas of the world where electrical power costs 75 cents a kilowatt hour, and they'll say, take my money all day long if you can provide the power. It is my position that if we have this lunar industrial site, that we can sell water all day long for $10,000 or $15,000 a kilogram for surface operations, which begins the buy down and the cost structure to where later for off-planet use, we can sell it for $1,000 or $300 a kilogram. So my concern is I love where George is going, but that's kind of like as the exponential curve starts to flatten is where George is at, but we need to pay for it now. And another thing we did, Gordon Woodcock and I did, we showed that with a lander, a reusable lander, we can carry 25 tons of metal in the lunar orbit and return to the surface for about, I think it was about 10 or 15 tons of water. So how much is that metal worth if I deliver that to geosynchronous orbit? So it's a slightly different mindset than what George has, but I love George's work, and I think George is where we want to eventually be. But I think in the beginning, we can easily charge $10,000 or $15,000 a kilogram for that water, and people will buy it all day long for science.
Hey, Dennis, this is George. Can I defend myself?
George, you don't need defending, buddy, but go ahead.
So what we did was try and initially tie it back to a market that already exists, which is moving mass, around Earth orbit. And the problem, you know, and I agree, you can charge a lot more on the surface of the moon because you're competing with people bringing stuff from Earth, and yeah, you can charge a lot more. 15,000 is probably on the low end, but that market doesn't exist yet, and it won't exist until you got a whole bunch of infrastructure on the moon. And what we were trying to do was figure out how to bootstrap it to sell into a market that exists now, to allow that infrastructure to get in place, and then you can sell it higher once you have stuff happening.
My contention is you got to have a whole bunch of infrastructure in place before you get any water for any purpose for anybody. So that's, you know, so this is the classic chicken and the egg problem.
Chicken and egg.
But the same infrastructure that you have for selling it cheap, we got to have no matter what. And my concern is that by boxing ourselves in
at a low price point,
we never get there, because that's been the same problem with solar power satellites. And I don't want to repeat that mistake, because the same infrastructure that you need for your cheap water, I got to have for expensive water anyway. So why not sell the expensive water? Because I'm telling you, and this is what we talked about at the Jermitson thing. Steve said, look, I've got 5 friends that will write $1 billion check.
Yep.
And so there are people that if we have a viable plan to where we can actually do something, I'm telling you, if we're mining water on the moon, NASA's going to buy it all day long.
Yep.
For science. Because there's a lot of legitimate science at the high price.
The lunar price, the lunar market.
At a lunar market price, because that is a order of magnitude cheaper than they can sortie emissions from the Earth's surface. So I think, George, both of us are right.
So what you need is NASA to stand up and say, I'm willing to buy water at that price.
Well, I agree with you, but here's the issue we're at. Everybody is wanting everybody else to go first.
Yep.
What we've got to have, and I'm telling you, I'm having these discussions right now with people of means. You got to have somebody to lead.
Yep.
And that's what we've got to have. But we've got to have a plan to where that it makes sense to lead. Right. And there are people who will put up the amount of risk capital we need. I'm telling you this, and telling everybody that is listening. There are people who are willing to put up the risk capital today if we have a plan.
We have a serious plan.
But if we start out saying $300 a kilogram, it's not a plan, because there's no, you know, you have A and then you're at K. We got to get B, C, D, E, F, G, and get the rest of the way there. And George, I love your ideas, and I think you're exactly right. And I think going to Mars, and I think going to the asteroids, if we build these interplanetary vehicles, there's the asteroid miners, and here's another thing to throw at you. If I can build an interplanetary reusable vehicle that goes between the Earth and Mars for $5 billion, that it costs $500 million per trip to go back and forth to Mars, I guarantee you I can sell that all day long.
Right.
And so that's part of the infrastructure as well.
There's a question from Doug Space. Is that Doug Plata?
Yep, that is me.
Doug, you have a question? Go ahead.
Yeah, Dennis or anybody, has there ever been a demonstration of the magnetic beneficiation of regolith, concentrating the nickel iron?
I've done it in my backyard. When I was 10 years old. I'm from Alabama, and one of the things I used to do as a kid, because there's high iron content in the soil, I throw a magnet into a pile of dirt and watch the iron coming, and those were iron oxide. And so, I mean, this is a no-brainer to be able to do this.
Dennis, we've all done that. What I'm asking is, with the nanophase iron coating the regolith, has anybody actually done it with regolith?
Yes.
Does anybody know?
Yes, Larry's done it. We've done it. This is, and the nanophase iron is great. We do this here on the Earth. We did it 200 years ago. I grew up in Birmingham, Alabama, where I used to watch this happen with pig iron. You take and you dump dirt and iron and high iron into a vat, and the slag you pull off. There's going to be a lot of slag in the beginning.
Yeah.
Who cares? But you're going to get enough metal to do what you want to do. And the thing, I'm a very practical purpose. I grew up around people, you know, my stepfather still mined coal using mule-drawn carts in the 1970s because it was profitable to do so. We can use more primitive techniques rather than trying to design everything to TRL 50 aerospace grade systems. Let's do what work rather, you know, there's an old military saying the perfect is the enemy of the good.
Dennis, I think, you know, nickel iron makes up 1% of the lunar highlands. It'd be nice if we could concentrate that more so we're not having melt 99% regular.
Absolutely. That's why God made magnets. And in the highlands region, you don't have anywhere near as much iron. There's very low iron content, so you're not going to have the nanophase iron in the highlands anyway, and it's going to be much easier to beneficiate the nickel iron meteoric fragments there. But also it's my contention from Moonrush that there's some big chunks up there as well. But I agree with you. But, you know, rather than talk, I want to look at things differently. And I want to make this statement. 170 years ago is when we started talking about putting a railroad across the country. And they didn't talk about all the problems, or they did. They said, but you know, these are all problems. We can figure it out. We can make it work. And they worked for 30 years, and they built in the middle of the Civil War.
Crazy.
For the life of the nation, we built a railroad across the country. So rather than focus on all the reasons we can't do something, let's focus on the reason how we can.
So what would it take to actually do this experiment? I mean, it seems like it'd be so simple to do.
Hardware on the moon.
Look, I have friends at JSC. I can go down there anytime we want and do this, but it literally is a no-brainer. So I'm not worried about that step. It would be nice PR and something real cool for Twitter, and we may do this in the next year or so. But to me, this is not in the critical path.
Other comments, questions?
Dan, this is Brad.
Brad, go ahead, Brad.
I got a simple one, I think, and the question I have, Dennis, is I think we got a pretty clear outline for what the business case for propellants could be. At least we have enough information to solve that model and solve for the cost that we would have to incur in order to make money given current prices. But what do you see the business case? You've been arguing for larger bits of infrastructure. And I really like your vision because it's you know, it's not little robots doing little things. It's expansive. It's industrial. It's humans. It's, you know, it's got all the bold things that we need to really go out and colonize space with some gusto. But you know, how do I break this down into a business case? And my challenge,
you don't. Okay, and here's the reason why. I understand. Go ahead.
Talk to me about construction and manufacturing.
Well, let's talk about the power landers to start with.
Construction.
I think we can put the power landers down for about $350 million apiece to start with, and we can put 10 of them there for between $2.5 and $3 billion. And that is the kind of numbers. I mean, right now, Rio Tinto or Anglo American, a big mine is between $3 to $7 billion today. The same order of magnitude is setting up an entire infrastructure system on the moon. Is what we're
talking with
doing.
People in the mining industry. I understand the cost, but I'm talking about the customers. Who are the customers for advanced manufacturing and for construction?
Well, right now, if you take a look at NASA's plans, there is money for science for doing sorties on the moon. Okay, that's in the current plan. We're talking about doing it for them 10 times cheaper. And it's already budgeted. There's already budgeting. We're spending $3 billion a year to build a rocket that's going to cost $1.5 billion to $2 billion for one mission. So I already see that. There is already that in play. And so we can take an easy extrapolation for that and say, NASA, If I'm a private interest and if I put this infrastructure there and can give you the same thing for 1/10 the price that they're already planning and budgeting to do, there's a customer. But I want you to think about something for a second. In 1862, when the Pacific Railway Act was written and passed, no one, absolutely no one, and I've read every document on this, not one single person had a business case for farming in California, providing fresh vegetables to the East Coast of the United States. But by 1878, over 70% of the rail traffic on the Intercontinental Railroad going back east was fresh vegetables. The concept of the refrigerator vehicle, they used to take and cut ice
off a lake
off the lakes in the Sierras so that they could ship vegetables and meat products. The San Joaquin Valley was unpopulated or was just cattle ranches before the railroad, but today over 50% of the fresh vegetables in our entire country come from that one valley. None of that was prophesied. So after we're there and after we're doing stuff with a base customer who we're already providing a product for 1/10 the price, we can branch out from there and go where George is and other people as well. Elon's going to buy this from us. Jeff Bezos is going to buy this. There are people of capital and means who will put the money up to make this happen.
The other thing is, you know, it's not like the government wrote, you know, billions and millions of dollars worth of checks. What they did is they underwrote the bonds.
Yeah.
And you got paid, you know, in bonds for the each mile of track you laid, and then the railroads were able to do that thing. They actually paid those bonds back.
Yeah, actually, yeah.
It took a while, but they actually paid that money back.
The way it worked, the bonds were written, the bonds were sold. The state of California bought a lot of those bonds, and states bought those bonds. Private investors bought the bonds. After each mile was finished, the federal government then wrote a check to the railroad companies that paid the bonds back. That's the way it worked. And so the Central Pacific was profitable all the way across, and they started sending a lot of rail traffic long before it was finished across the country. They sent it to Sacramento. The first line was from San Francisco to Sacramento, then Sacramento to Reno, then Reno.
But Dennis, this is Alex Ignacio. That financing model won't work now. And I understand.
Well, you know, hang on, Alex. I love you to death, but "won't" is not a word that we don't know if that's going to work or not. And I'm going to interrupt you here because we're already over our time. But take a look right now. I'm reading a book right now. I've just started it on the U.S. Merchant Marine. And the U.S. Merchant Marine was financed by the government, built by private industry for the government, and then the ships were sold at 1/10 the cost to build them in order for us to build a merchant marine fleet. If it is a decision by our government that we want to support a move into space, and if you listen to Jim Bridenstine, if you listen to Mike Pence, if you listen to Donald Trump, this is what our current government wants to do, is to help commercial enterprise, not the great von Braunian state-directed leap into space, but a more commercially focused effort. And I can tell you at the top level of DOD, it's what Mike Griffin wants. This is what everybody wants. And so I don't take no for an answer.
And by the way, we're just about out of time. Let me see. There's a couple people have their hand up. Dave Chevron, you have a question?
Yeah, well, I just got a comment. Can you hear me all right?
Yeah.
You know, we just kind of finished up doing this study with public-private partnerships and economics model that Brad Blair, Hoyt Davidson, myself, and one of my students had worked on. And, you know, it seems like that has the kinds of variables in it to assess different kinds of public-private partnerships, different amounts and extents, whether the government puts in agreements to purchase material, to have a strategic materials reserve for the metals, to have the commitment to buy or the assistance in developing the technologies. So we have a model that I think would be very useful to evaluate some of these different kinds of scenarios. And also, we included multi-commodities in there, so we can look at not just water, but we can look at all kinds of things: the oxygen, the aluminum, the iron, you name it. I think Brad's pretty much got it in there. So, I think this is the kind of analysis that we need to maybe, see if we could collaborate on and try to get, some better insights into how to kickstart this thing.
Yep, that's great. I'd love to see it.
Okay. Brad, are you willing to work with Dennis on that?
Yeah, and one of the things that I'll say, Dave, is that, the amount of money we got paid for that study pretty much paid for the slideshows and the report we may put out on that, but the model is pretty much something that you and Hoyt and I put a lot of our own sort of sweat equity into, and at this point in time, it might have better value as a sort of a proprietary holding. So just saying that for right now, and the issue is how do we sort of connect and interface with those people of means and capital that Dennis is talking about, and having detailed models that and there are several. George has got some really good models too, and he understands the customer a lot better than I do. But the combination of those, I think, is really best used to get the attention of people and how we can actually make money in this deal. So.
Yeah, well, and the intent was to be able to help inform NASA on different options to try to proceed with public-private partnerships.
Yep.
So, I think we ought to.
I think we explored a lot of that space in the PowerPoints that we've been putting out there and publishing, and we have an option agreement right now to publish a nice report on that and put a bow on. Lynn and Dan will be happy to take our report and put it up on their website.
Sure,
but it's,
sure. No, we're happy to do that, Brad.
Yeah, we've got to start doing some of this, because I can tell you right now, I paid and I put all my sweat equity into writing my book. Nobody wrote me a check for that. Nobody wrote me a check for doing this PowerPoint right here. Nobody's covering my time for doing this. Consider it a marketing expense, because I literally wrote my book as a marketing expense, and we've got to be a little bit more collaborative out there, and we've got to let this stuff out. I believe in proprietary, I believe in IP and all, but at some point we've got to be willing to put it out there and see where the chips fall.
Any last comments, questions? We have a couple of there's a couple of questions on the chat line, but
just one last thing, Dan. Also, I want to mention Hoyt has proceeded to put together a paper on OSPIC, an outer space investment kind of planning thing based on the old OPIC. So, that's another thing we ought to be looking at. So go ahead. Sorry.
Send around a link on that, Dave. That'd be good to the group.
Okay. Yeah, sure will.
Thank you.
No, and I want to apologize as well to my good friend Alex Ignatieff. Alex is one of my favorite people in the world, and I apologize for cutting you off, Alex, but I really and truly, I think this is not 10 years ago, it's not 20 years ago, it's not 30 or 40 years ago. The world is changing, and I think we should look
at opportunities,
much more at what we can do, and not what we can't do.
I agree. The question often is, what's the business case? Because we've talked to people with money, and the answer is, what's the business case?
I think that's actually, and you're right. The government business case is a completely different question than a industrial business case.
Yeah, so. But I can tell you that there are people of means out there right now.
Yes.
That if we have a plan, it's just like Elon. What was Elon's business case for building a greenhouse on Mars? What was Elon's business case right now for Starliner? He
doesn't have a business case.
Yeah. What is Jeff Bezos' business case? Okay, there's a speculative business case there. But at the bottom line is these people have the money. This is where they want to spend it. I will tell you right now that there are people, there are patriots in this country that if we have a plan that has a return at some point in the future, they will put money up. And it's time for us to get together and start putting these plans out there so that people can look at them to where we have, because literally we've had an incredible mindset change in the past 10 or 15 years in this country and in the world. We need to, for those of us who have the scars on their heads, we need to remove those scars and go for it again.
And with that, let me call it a quits. Thank you very much, Dennis, and thank you everyone online. And again, we will look forward to having folks next week. So thank you very much. Bye-bye.
Great presentation. Great presentation.
Great. Thank you, Al. Thank you, everyone.